Hello again, everybody, and welcome to another Geo-Institute live stream. It is the final day of July 31st, and later today you can look at all of our social media and you'll see a beautiful graphic featuring Santa Monica Pier and a list of all the things that are coming up for you from us in the month of August as we plow through this summer of live. My name is Brad Keeler. I'm the director of the Geo-Institute, and thanks for being with us once again as we take you behind the article in GeoStrata Extra. If you haven't heard anything about the Geo-Institute, if you don't know anything about us, after you watch this interview today, head over to geoinstitute.org, and there you will find out all kinds of things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and 9 out of 10 people, actually it's higher than that, it's more like 99 out of 100, always say that they do. So you should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. Of course, this is GeoStrata Extra, and at any point during your life, really, you can go over to readgeo.org, and this is what you will be faced with when you reach that page. You'll see the current issue of the magazine. You can click around to all the different content that we have. You can go into the page view and look at things that way as if you're actually holding the magazine in your hands. You can go over here to the issue library, and when you do that, you'll see all the back issues that we have available to you, so you can check out your favorite Geo Legends episodes, go back and see that thing in Core Bits that you missed 3 years ago about a new hire that Keller made, or anything else you might want to do in the magazine. Of course, it comes out 6 times a year. We will have a brand new issue tomorrow. We'll mention that at the end of the episode as well. But now, one of our we'll call you an esteemed editor, Ken. One of our esteemed editors is here to take you behind an article from the June-July magazine, and all the way from Buffalo, New York. It's Ken Fishman. Ken, take it away.
Thank you, Brad. Well, the theme of our last issue was mine waste geotechnics, and today I'm going to talk with Jorge Macedo, who is one of the authors on a paper which is Liquefaction and Tailings Storage Facility Failures. There were 7 articles in this month's issue of the magazine, and out of those 7, 4 of them dealt with tailings, plus we had 2 commentaries, and each one of them also dealt with tailings. So this is really a great addition to those descriptions of tailings. And as we start out, Jorge, why don't you give us a little brief overview of the paper, and then we'll go and dive into it a little deeper with some questions.
Perfect. I'll share my screen and we can take it from there. And just give me 1 second. So hopefully you can see my screen.
Yeah, here it is.
Okay, so yeah, I kind of following your suggestion, Ken, I prepared a little presentation to summarize the article. I'm going to be focusing on I would say, the failure components. In the article, we have other components related to several aspects. But before going into that, I want to thank you, for actually making me aware of the GeoStrata articles. I recall that happened during one of our conversations when you visited Georgia Tech for our SOARS symposium. So thanks for that. And also, I want to thank the Geo-Institute for this opportunity. So my name is Jorge Macedo, and I'm an associate professor at Georgia Tech. And I'm also the founder and chair of the Tailings and Industrial Waste Engineering Center. So let me go with a little bit of, I would say, material that I want to just show to start the discussion and to promote the conversation. You know, one of the words on the article, keywords, is liquefaction. So I wanted to kind of start providing a historical, very quick overview on the motivations for why we are kind of dealing with that phenomenon. What you're seeing on this slide right now may be familiar for many. This is the Fort Peck Dam that failed on September 22, 1938. So you can see the type of the failure. Not sure if you can see my mouse, but I think that the slide is illustrative enough. The photo is illustrative enough for that. So this photo, 1938, remember that year, was associated with a phenomenon known as static liquefaction. So remember that keyword, because you will be hearing that a few times during this initial quick presentation. So this is 1938. So, and about that time, and what you're seeing right now over here is the Franklin's Falls Dam, and that is kind of attributed to work at the Corps of Engineers on the U.S. A concept started to be put forward, and it was how to make dams resistant to that to liquefaction. And what you are seeing here on this little inset over here are just some classical tests from
Jorge, your slides are not flipping. I think you have to go into presentation mode.
Oh, let me check. Sorry about that. Can you confirm if you can see them now?
Yeah, now I can see Franklin Falls, 1935.
But we're not seeing it in presentation mode. We're just seeing your screen as if it's in PowerPoint. We have the banner up at the top and everything.
Oh, let me see.
My guess is that you have two monitors set up.
I only have one, actually.
Oh, okay.
Yeah.
Okay, so you can flip through the slides this way if you'd like. Just make sure you remember to do it. Or if you unshare and do it again, go into presentation mode and then share, and it should be fine.
Yeah, let me try unsharing to see if that works, and we'll see if it's not working. I'll just do it that way. So I just stop sharing. Let me go back to the Teams call, and I'll share my screen again. So let me see. Okay, I'll put, let me see. This should be presentation mode. Is it better now or still an issue?
We're still seeing the whole screen, so this is fine. Just go through the slides like this so everybody can see them.
Yeah, no, thanks for letting me know. Okay, sorry about that. Not sure, some technical issues, something maybe happening there. But anyways, what I was mentioning is kind of, we're 1935, remember, and I just showed you the Franklin's Fall failure in 1938. So about those years, there was the concept of, creating earth systems that are resistant to liquefaction. Those discussions started to be put forward. And what you're seeing over here is, famous tests from Professor Casagrande. And the concept of having, materials that are loose and behave contractive, and materials that are dense and behave in a dilative mode, that's the terminology that we use as geotechs, kind of started to be coined. And I don't want to get into too much technical details, but pretty much a dense material is one that is over here, and is going to be, developing a peak on the shear strength, and then you are going to be having a loose material that's going to be here. And they are going to be kind of coinciding at a place of large deformations that I usually, when I describe that to my students, I say that that's the happy place of the soil. That's, where the soil wants to go, no matter what's the initial condition, no matter what's the initial fabric, if you believe on the critical state theory. But the idea was that, if you want to have a structure that is resistant to liquefaction, you want to be on the dense side, in very simple words. This is 1935. Now we are going to be kind of moving in time, and I'm taking you to 1994, and this is South Africa, and this is Marisprut, and it's the Marisprut failure. Again, several studies related to that, but it was associated with static liquefaction again. The same phenomenon I was talking about on 1938. Some, characteristics of the failure.
Advance your slide. You need to advance your slide. In Franklin Falls.
It is right now on Marysprut. What slide are you seeing, Ken?
We are still seeing Franklin Falls. That's what maybe the best thing to do is just go back to your regular slide view and flip through that way. And there you go.
Yeah. Let me actually try something else very quickly. Let me know if that works. Are you seeing?
I think we got it.
Yep.
I think we got it.
Okay. Yeah. Good. Okay. So now we are 1994. It is a Marysprut failure. You can see some of the features of that failure. Fortunately, 17 people killed, 80 houses destroyed, significant amount of tailings released, and again associated with the phenomenon of static liquefaction. So let's keep moving in time, and now I'm taking you to the United States, and this is the TVA. This is a failure in the TVA, that's Kingston, corresponding to the Tennessee Valley Authority. This is not, strictly speaking, I would say, a tailings dam, but it's a coal ash deposit. So there are several similarities, and guess what? Again, the failure associated with the same phenomenon, static liquefaction. So now I'm taking you to 2014. This is Canada now, and this is the Mount Poly failure. You see here on the left photo over here, you are seeing the condition before the failure. So this is kind of the tailings dam, and you can see the tailings being stored over here. You can see the brown color here, and the retention basin over here. And then on the right side, you can see the aftermath, which is now the tailings have kind of invaded the rotation basin. And now they are even going into the body, the water bodies that we have around. So that's now in that particular case, the response was more complex, or the failure was more complex, because it was associated to the interaction with some layers in the foundation. So we could argue, there are debates about that, but we could argue that it's a system level response. But again, static liquefaction was in the middle of the discussions. So now I'm taking you to Brazil. This is Fundão, 2015. This is a very well-known failure. Again, the term static liquefaction was also part of the key discussions after this failure. And now we are on Kedia. This is Australia, 2018. This was also associated with static liquefaction, but similar to Mount Poly, there was also system-level response. Have kind of layers on the foundation interacting with the tailings that are stored on this dam, and there is a ITRB report that was is publicly available that is discussing in detail the mechanisms and the system level response, so you can check it out. This failure was more limited. Some actually refer to it as a slump rather than a significant, uncontrolled release of tailings. And now this is 2019. For those that work with tailings facilities, this may be very, I would say, familiar. But I'll just play the video very quickly for those that may not be familiar. So this is the Brumadinho, the so-called Brumadinho failure, and just take a look, on how liquefaction looks like. Yes, the first time I look at that I was really shocked and impressed. And I would say also scared. So just look at this, amount of materials that are being released in an uncontrollable way, in a very rapid manner. Again, many discussions about this failure. There have been several reports. Peter Robertson has been the chair of one of them. There has been work at also at the University of Catalonia in Spain. But static liquefaction, again, at the core of the discussions. So, philosophically, I would say the point to discuss over there is, before I go to my next slide, is we had static liquefaction, discussions on 1938 for PEC dam failure. Now to 2019, 80 years after perhaps, it's still, part of the core discussion. So it's kind of, someone may argue, someone that is not perhaps very active on engineering, an external observer may argue, what's going on? So now, there have been several failures, as I mentioned, but there have been also several cases of good performance, especially in terms of the seismic response of tailings dams. I'm showing you here just a quick example. This is after the 2010 magnitude 8.8 Maule earthquake in Chile, where most dams in Chile actually perform well. So there is a lot to learn from the failures that have happened, but also a lot to learn from the, I would say, success performances that have also been occurred, especially on, a magnitude 8.8 is a massive earthquake, as those working on earthquake engineering know. So now, a little bit of philosophy over here. When I was on practice, I was fortunate to work in practice for about 7 years, and I was fortunate to work with Dr. Ken Fishman and also Mike Jeffries. And I just took, a paragraph that Ken wrote on his last paper. Unfortunately, he passed away on 2015, if I'm not mistaken. So he wrote the following. When speaking about Fundão, remember Fundão happened in 2015, so this was written shortly after that. And Ken wrote on one of his last papers, that was a keynote lecture as part of one of the events at the International Society of Soil Mechanics and Geotechnical Engineering. And he wrote, we have already drawn attention to the parallels of Fundão with the concerns of the Corps of Engineers 80 years earlier. Here, he's referring to 4PEC. Then he said, or he wrote, it is the lack of teaching of critical state concepts to geotechnical engineers and the application of rigorous mechanical approaches that has caused this problem. So, this could be interpreted in different ways. I have had several discussions with people in the industry, people in academia, on how this could be, I would say, interpreted, reflected, and we can have many discussions perhaps on the part of the questions, but I wanted to share this with you. And something else I wanted to share is, this is taken now from a paper that Mike Jeffries wrote on 2021, expanding on previous work of Professor Morgenstern on 2018. Both Professor Morgenstern and Jeffries, Mike Jeffries, are, I would say, renowned experts on the tailings industry, and they were discussing the root causes of tailings impoundment incidents. And what you can see here is, different failures, the years of the failures, the places, and then you can see basic causes and 3 groups: engineering, operation, and regulators. So, and this check mark is kind of an interpretation on what was the driving factor. You can see that there are more kind of marks on the engineering side, which, to some extent is consistent with what Dr. Ken Fishman was mentioning in 2015. Dr. Ken Fishman referred to the lack of critical state soil mechanics concepts, but, looking at that in a broader perspective, that could be also interpreted as engineering being, I would say, appropriately applied on the design of tailings storage facilities. Again, that's up to discussion, and my motivation here is just to put forward that discussion. So now, one aspect that you have, or one word, or one terminology, or one phenomenon, if you want, that you've heard a lot during this presentation is a static liquefaction. So before going into the questions and the discussions with Ken, I wanted to make a couple of additional remarks about that. What you're seeing on this slide is what I would be calling the classical, definition of a static liquefaction, which, if you have undrained tests in the lab and you plot the stress path, this is just the deviatoric stress and the mean effective stress. and then you locate the upper, points of those stress paths. You can define a line, and then by defining that line, you are going to be having a so-called region of potential instability. And some ANS refer to that as the instability line. This is not new. This is 1999, and this is attributed to Professor Lade. So in a more, I would say, common space, when you have the deviatoric stress or axial strain, this is just the peak of the response. This is a very classical definition. But what I wanted to highlight here is something related to what happened on Fundão. So let's say that you don't have an undrained loading, but now your loading is going to be purely drained, okay? And these stress paths on the right are representing that loading. You are seeing kind of letters here, A, B, C, and D. The entire loading is going to be just drained. There is no, on the triaxial cell, the valve is open, so everything is drained. But let me play the video, and then I'll make a couple of comments. And this video was created by the panel of experts, the forensic panel after the Fundão failure. So I'm playing the video already, and you may notice that there is no movement at all yet on this, sample that is on the triaxial cell over here. But pay attention and then see what happens. Now, you saw that, like suddenly, you saw that it was not moving, and then it's kind of moving, kind of abruptly. And that is like, this could be attributed, sometimes I have had discussions on what's the best terminology for that, but in a broader sense, that can be also attributed to a static liquefaction. So a static liquefaction in that case, it's happening when you have the stress path going from B to D, and typically we say that it's associated with a stress relief stress path, where you are going to be having that at point C, instability is triggered, and then the formations are kind of happening abruptly, and they are going to be accumulating significantly. And everything here is happening under drain conditions. So very difficult to monitor that. You may not have any warning before that's happening. You may not see excess pore pressures, for example, if you have piezometers that are installed over there. So it's a very difficult failure mode to anticipate. So the takeaway that or the message I wanted to send here is that when you're thinking about static liquefaction, it's not only drain loading. So here you are seeing that, static liquefaction, if we are not picky about terminology, could also happen under fully drained conditions. So that's relevant. For example, this is another video that was put forward by the Fundão panel. And then what happened there, this is the tailings deposit. This is an upstream tailings deposit. You have fine slimes over here, which are compressible. So, and then you have the sand tailings over here. Those fine slimes are going to be pushed because of the weight that is above. So it's like a toothpaste, if you want. And they are going to be moving in the direction of the arrow. When they do that, they release stresses. And when they release stresses, the stress path over here is going to be going to the left, and eventually we are going to be having, a failure or liquefaction. And that, for example, was the mechanism that was associated with the Fundão failure in 2015. So again, just a general introduction over here. In our article, you can see, more discussions about liquefaction, but also the importance of having a multidisciplinary perspective when you're dealing with tailings storage facilities, as this is only a specific aspect. Tailings storage facilities are quite complex, and there are several considerations that need to be considered. So with that, Ken, I can stop here, and we can go, I'll stop sharing my screen, and we can go to any questions either from the audience or from you.
Okay. Thank you, Jorge. I just want to get into a couple of introductory questions, and we'll kind of get into some background history and issues, etc. But it appears that your research is really at the intersection of mining geotechnics, extreme events, and artificial intelligence. What piqued your interest in these areas?
Yeah, no, that's I would say a very interesting question. In terms of extreme events, my interest actually started when I was a kid. It just happens to be I was born in Peru, and the region where I was born is known as Yungay. It's a city in Peru, and that city was affected by the deadliest earthquake on the entire Peruvian history. That was in 1970. So when I was a kid, I was hearing histories about how devastating was the earthquake, and that earthquake was actually connected with a massive landslide that wiped out the entire city. So since very young, I was, very curious about extreme events and earthquakes in particular. So now, when I started that was the interest in extreme events. Now, in terms of mining geotechniques, in Peru, I did my undergrad in Peru. When you get your professional license, or the equivalent of a PE license here in the US, you need to do a thesis. So it's kind of a little research work. So my thesis was related to the seismic performance of a dam. And that work opened some opportunities for me to work for Golder Associates. Golder Associates is not anymore active. It was bought by WSP now. So, but in Peru, or I would say in South America in general, when you work as a geotech, most of the work is for the mining industry. There are, the biggest mining projects perhaps in the world. So as an engineer, most of my work was related to tailings dams, heap leach pads, and tailings geotechniques in general. And those projects were very multidisciplinary, very, I would say, complex too, and I think always curious. So that's how, I was also attracted to the mining geotechniques area. And in terms of the last aspect you asked, which is related to AI, when I was also, I would say, kind of deciding what to do at the university, because in Peru you need to apply to different careers. Actually, I was hesitating between computer science and civil engineering, because I always enjoyed coding, math. I really, really like math, and I took the decision of following the civil engineering path, but I was always attracted to computer science. And now I guess I have the chance to really go back to those interests, and also looking into AI, which is kind of, I would say, offering significant opportunities to advance not only tailings geotechniques, but several areas in general. So I'm enjoying that intersection of actually mixing my interests on extreme events, mining geotechniques, and also AI.
Kind of following up on that then, so you put those together, and how did you get started with tailings storage facilities specifically, these TSFs?
Yeah, as I mentioned, that kind of happened during my years as practicing engineer when I was working for Golder Associates. My first work as a consulting engineer actually was to go to do some field work in a tailings storage facility, and I was exposed to the complexity of those facilities. And it's not only a geotech work. Actually, I would argue that one of the key components is actually water management. It's maybe as or more important than the geotechnical components alone. So very early in my career, I was exposed to TSFs. And then, one interesting thing at Golder was that the projects were quite high, quite large projects. So as a young engineer, I was exposed to different, environments and different challenges. And that was really fun. So I kind of enjoyed that and picked my interests.
Probably it's related to the multidisciplinary nature of the topic, but a lot of the articles had multiple authors, and you have 6 co-authors on yours. I understand that you interact with each of them at the Tail Inch Center. So tell us a little about the center itself, from where all you guys come from, and what's its missions and activities.
Yeah, no, absolutely. Indeed, we collaborate with the co-authors of the article that we put forward at Tail Inch. TAILENG stands for Tailings and Industrial Waste Engineering Center. It's a faculty consortium with faculty at 4 different universities. It was founded at Georgia Tech. It has also UC Berkeley, Illinois Urbana-Champaign, and Colorado State University. From the list of co-authors in the article, Professor Jonathan Bray and Professor Scott Olson are part of the steering committee. And we have also Paul Ridlen, who is at NIPISOL, who is an industry leader. I would argue very active at ICOT as well. And he's kind of bringing, the industry perspective and sharing decades of expertise. So that was very, very useful. Then Christina Winkler and Kim Morrison, they have been actually on the owner side for several years. Christina Winkler worked for Anglo America and Kim Morrison worked for Newmont, and they are part of the advisory board at TAILENG. They have a unique perspective from the owner side. They have moved now to consulting, but they also bring decades of experience on tailings engineering. So it's been actually an honor to for me to write an article with such a renowned group of experts. And going back to TAILENG, the mission of TAILENG is to advance the state of knowledge and practice in the design, operation, and closure of tailings and industrial waste storage facilities. And we do that at TAILENG through innovative, fundamental, and also applied research and educational activities. You can look at our website, on what we do specifically, but I may highlight a couple of things. One is that we really want to elevate the standard of practice, but also we want to follow, a proactive approach. We don't want to be only reactive on what has happened, for example, on the recent, on the failures during the last 2 decades, but we want to really look at the future as well. So that's one of the, I would say, things I wanted to highlight. The other one is that we firmly believe that we need to, contribute to create the next generation of tailings engineers. So those are 2 aspects that are really, really key at TAILENG. And in general, what we do at TAILENG is to engage with mine owners, also operators. We engage with consulting engineering firms, regulatory personnel, and also in general interested members of different technical communities to advance the practice on waste residuals management focus on tailings.
Thank you. I'm going to back up just a little bit and get into a little bit more of the background about tailings. And I'm going to combine a few of our questions here. But basically, what are mine tailings, and what different disciplines are involved in the design of a TSF? And are there any distinct similarities or differences between mine tailings and other types of dams, like earth dams? If you're a geotechnical engineer and you're an expert at design and analysis of earth dams, is there a way to cross over here, or do you have to get a lot more background in some other areas, hydraulics, etc., in order to start working in this area?
Yeah, no, I think there are a lot of angles on that question, so I'll try to, I guess, address them as best as I can. But let's just start with tailings, and just a general, perhaps simple definition is tailings are basically the leftovers after we take the valuable part of, I would say, of an ore. And those leftovers need to be stored on structures that are designed based on engineering principles, and those are the tailings storage facilities. So now, regarding the part of your question on what disciplines are involved in a tailings storage facilities, it's very, very multidisciplinary. So, for example, you can find process engineers to kind of deal with the as the name suggests, with the processing of the tailings and transportation aspects as well. There are also mechanical engineers that are involved. We have structural engineers that are also involved on designing the structures that are going to be supporting the overall, tailings infrastructure. We have geologists, we have hydrogeologists, hydraulic engineers, environmental engineers, geochemical engineers. Also, it's important to highlight the role of the social sciences as well, because sometimes, that's needed in terms of potential impacts that TSF may have on society. So I hope I'm not missing other important areas, but it's very, very multidisciplinary. So, and this is actually quite interesting. So now, in terms of I think you asked also something related to the similarities between more traditional, to say it in a way, water dams and tailings dams. I would argue that there are similarities, but also important differences. For example, in terms of similarities, air dams and for water purposes and tailings dams both have to be designed relying on fundamental principles on geotechnical engineering and hydraulic engineering and all the other aspects that I just mentioned. In terms of differences, I believe I could highlight few in terms of the purpose, construction and also operation. In terms of purpose, more traditional dams are built to store water for several, purposes. Tailings dams are storing the waste materials that are coming from mining operations. So in terms of construction, typically water dams are constructed, comparatively speaking, like faster compared to a tailings dam. A tailings dam, however, it needs to accommodate continuously the residuals that are coming from mining operations. So typically, it's going to be built on different stages, and that's going to be happening over several years. So in that context, the operational management can be also, I would say, more complex and need to have some flexibility. Overall speaking, in that sense, operating a tailings storage facility is more complex, in my opinion, compared to a water dam. Those are some parallels that can be drawn, Ken.
Thank you. You gave a presentation when we started, and you kind of went through the history a little bit of some of the failures of TSF, some of them fairly recent. Can you comment about lessons that may have been learned from a geotechnical perspective from some of these case studies where things did not go so well?
Yeah, so I think perhaps I may just highlight and echo a little bit on what Dr. Ken Fishman wrote on his last paper, that probably we as geotechnical engineers, and I'll try to, I would say, narrow down my response and perspective on geotechnical engineering. I think it's important to go back to fundamental principles in soil mechanics, because we should not forget those principles. They apply to mine tailings, and critical stage soil mechanics, for example, which is one of the, I would say, core frameworks applied to tailings geotechniques, is relying on fundamental principles of soil mechanics. So I think one of the lessons is to really go back to the fundamentals and really think about the mechanistic aspects of soil mechanics, because concepts like dilatancy, soil strength, and comprehensibility, which are key to assess phenomena like static liquefaction, perhaps are not as emphasized as they should on a graduate education of a geotechnical engineer, for example. I have had many discussions with people like Mike Jeffries, for example, on the relevance of critical stage soil mechanics teaching for geotechs, and even how many programs on the US are having robust critical stage soil mechanics courses. So there are many debates around that. But I believe that having those concepts are fundamental for a geotechnical engineer that's going to be working as a tailings engineer, because those principles, and drain responses, contractive behaviors, all of that's going to be guiding how engineers are going to be taking decisions. The other aspect, perhaps, to highlight is the so-called performance-based design, which is being also put forward by the new standards on the new global industry standards for tailings management. And that pretty much means an integrated, assessment where different aspects are considered based on performance targets. That's very, I would say, traditional, for example, on earthquake engineering, where the so-called performance-based earthquake engineering design has been applied for decades, but expanding that into aspects of static liquefaction or even other, operational aspects or design aspects, I think is something, that the recent failures are kind of reminding us as well.
Thank you. You actually kind of answered the next question already about performance-based design, so I'm going to jump into the issues a little bit. Do tailings from different sources exhibit significant differences in terms of character and properties? What parameters are most useful to characterize tailings? Like when it comes to soils, we look at gradation, Edinburgh limits, things like that. And how are these differences considered in the design, construction, and operations of tailings?
Yeah, no, I believe, fundamental principles are going to be key, as I said before, but things to highlight, for example, mineralogy, very, very, very important. Different ores, different mine tailings coming from different ores can be having different mineralogical aspects, and that's going to be key on characterizing them properly. Mechanical properties related to the latency, strength, compressibility, very, very important as well. Also understanding, the role of the fabric. For example, my colleague at Georgia Tech, Carlos Santamarina, he wrote an article on Science where he was highlighting the effect of early diagenesis on the recent failures, and that's going to be intimately related with microstructural aspects that are I would say present on mine tailings. So kind of answering your question in a general way, yes, different ores are going to be, mine tailings from different ores are going to be having different properties, but I think we should be having a unified framework to characterize and understand them. Mineralogy, very important. Geochemistry, very important. Mechanical properties like dilatancy, strength, compressibility, very important. And in my opinion, we should be departing from, yes, empirical approaches. They have a place, of course, but most of, empirical correlations have been put forward for sands and clays. Tailings are typically in the middle, typically are silts. Sometimes are having some, aspects of clays, other times some aspects of sands, but they should not be, in my opinion, characterized as empirically. I think it may be one of the reasons why, if you go back to industry and you look what's the prevalent approach on tailings engineering, is the critical state soil mechanics. That's not only on the academical side, but the industry is using that approach for many projects. When I was at Golder, for instance, working with Mike Jeffries and Ken Being, talking about more than 10 years ago, perhaps, that was the prevalent approach that we were using, like talking about in 2010 or something like that. So now that has continued. If you look at for example, the forensic reports about after recent failures, most of them rely on critical state soil mechanics, on the critical state soil mechanics framework for evaluating the consequences of the failures, or the reasons for the failures, I should have said.
You spent a little bit of time in the article talking about the use of CPT and the parameters you get from CPT and using that as an in situ investigation technique to help to characterize the tailings. Are there other in situ investigation techniques that have or can be applied? What are the limitations to the CPT? And is it possible to get good undisturbed samples that maybe could be tested in the lab and give parameters, or do you try to somehow recreate, remold your samples in the lab somehow to try to represent field conditions? What's going on in that area?
Yeah, no, starting with the field investigations, there are different techniques actually. The CPTU is perhaps one of the most common techniques used in practice, but there is a variety. So geophysical methods like multi-channel analysis of surface waves, refraction test, or any geophysical methods measuring shear wave velocity and P wave velocities are informative. Electrical resistivity, it's also used quite commonly on tailings projects. More recently, nuclear magnetic resonance is also starting to be used. Nuclear magnetic resonance, I'm not gonna get into the details, but it's pretty much what doctors do on MRI. It's the same principles of MRI applied to nuclear magnetic resonance. And the idea is that measuring the amount of protons that you may, either in protons in a medium, and based on that, it can provide, estimates of water content and saturation. I think there is a question on saturation, by the way, in the chat. So there is a variety of methods that can be used on field investigations. The vein shear, I was forgetting the vein shear. So vein shear, very important also to look into peak and residual strengths. So I think we should be looking at the characterization of mine tailings from different angles. So one technique is going to be giving, one piece of information, and all of them collectively are going to be allowing to really have, a better knowledge of the material we are dealing with. It's like when we go to a doctor, right? We have different tests, and those tests are kind of complementary to help us to assess what we have. Now, regarding your question of the quality of samples, that's a tricky one. That's a difficult one because, tailings are compressible material, and sampling them, with high quality from the field is very challenging. We have right now an existing effort at Georgia Tech where we have been getting samples with different techniques. The traditional and more common technique, Shelby tubes, for example. We have been using also gel push. That is something that was put forward by the Japanese, actually, which is adding a coating gel around the sample to minimize friction on the sides. And also the hydraulic piston samplers like the Dames and Moore. And we are kind of comparing them to see what are the differences. So hopefully we are going to be releasing that. This is ongoing right now, but I guess what I can say is it's very difficult because densification is going to be happening very, very quickly if you don't treat the samples like with extreme care. Actually, each sample, as Professor Bray always says that. He says that each sample has to be, I would say, taken as your baby. From the moment you take it from the field, to the moment it's going on the lab, many things could be happening. So we are treating them, our samples, the ones that we have collected, literally as our babies. We'll see how everything comes up, but very difficult and challenging task to get undisturbed samples.
You've mentioned several times the importance of critical state soil mechanics in those principles are important to apply to understand the behavior of the tailings. But specifically, what constitutive models are you able to use that kind of incorporate these critical state concepts for the analysis of the impoundments under either dynamic or quasi-static loading? What are the features of these models that make them well suited for tailings?
Yeah, there are a few options out there, but I always say that perhaps more important than the constitutive model that an engineer would be selecting to doing an analysis is an appropriate characterization and an understanding of the material, that is relevant for the analysis that's going to be conducted later. if the characterization is not, appropriate, we don't have, the enough inputs or in general enough information, garbage in, garbage out. We can put anything into a constitutive model or into a computer, and we may be just getting misleading results. Having said that, typically there are two, I would say, type of modelings that, in terms of the physical stability, that are conducted. One is assessments for static liquefaction. I think NORSANT is one of the most perhaps adopted models on engineering practice, because it's very, I would say in my view, very elegant. Most of the parameters that NORSANT uses can be explained, or can be linked to experimental tests. So NORSANT is, I believe, one of the prevalent models out there. SUNNYSANT is another option that can be used for static liquefaction as well. It's a little bit more difficult to calibrate compared to NORSANT, but if you have enough information, SUNNYSANT can be also a great option. On the seismic side, I believe that the models that are dominating practice are the models from UC Davis, PM4SANT and PM4SILT. Those models have been calibrated specifically for reproducing the cyclic response of materials in general. They can be, in my experience, when they are used for tailings, there has to be enough information specifically to inform the secondary parameters, but I think they are kind of dominating in practice as of now.
Thank you. Moving on a little bit more into some recent actions, I think one of the points that you make in the paper, and several other authors in different articles throughout this issue kind of mention, the need for more trained people, to be able to do this analysis and to design and understand the operations and everything with these TSFs. So do you teach any courses dealing with mine tailings and TSFs, and are these students assigned projects with realistic case TSF scenarios?
Yeah, so one of the, I guess, strategies that I have been following in Georgia Tech is to put a significant component of mine tailings on the courses that I'm teaching, and I'll tell you in a little bit about a new course that I'm creating too. But starting with the courses that I have been teaching, let me just offer a few examples. I do teach, for instance, the critical state soil mechanics class at Georgia Tech, and the project in the class considers actually evaluating the recent failures that I was talking about in the presentation. So students, for example, are reading and analyzing the forensic reports after recent failures, Fundao, Kedia, or others, and they are doing their own analysis using critical state soil mechanics principles. So the fundamental principles are connected with their application in practice. And by doing that, they kind of go through the journey on how to assess the physical stability of a tailings storage facility. Now, that's an example of a graduate class. Another example of a graduate class is in situ, the class that I teach on in situ soil characterization, where typically I provide students with data on mine tailings, either CPTs, bench shear tests, or other tests, and they look into the data, and using a mechanistic perspective, they characterize aspects of the data. On the undergrad classes, I was teaching the intro to geotech class at Georgia Tech, and I used the case history failures that we were discussing at the very beginning, kind of to, first of all, to illustrate the complexity of geotechnical materials, and also to pique the interest of young students on a career in tailings engineering. In terms of developing courses, something that I've been doing more recently is to develop a class in mining geotechnics that is considering TSFs and also heap leach pads and the overall, additional aspects related to the geotechnical connections that we have on mining geotechnics. And last but not least, perhaps also I should highlight the role of AI. At Geotech, we are pushing, different AI initiatives. I teach the data analytics class it's an undergrad class that is focused on machine learning and AI. And typically, something that we have from TSFs is a lot of data. If you think about the CPT that is done every 2 centimeters and is just going to 20 meters, that alone is, I believe, about 4,000 points. So if you have 10 CPTs, that's 4,000 multiplied by 10. So it's a lot of data. So I use that also to pique the interest of students on evaluating, mine tailings related aspects, but connecting that with also more, I would say, trendy topics right now, like AI, for example, machine learning and data analytics.
Thank you for that. We're moving on a little bit to seismic analysis and design, but I think at this point I just want to remind everybody in the audience that if you have any questions, go ahead and submit them to the chat. I do have 2 questions that were submitted by Nadi Wallstorm, and they kind of relate to seismic analysis and design. So I think I'll give them to you now, Jorge. They look pretty clear. But the first question is, saturation levels greater than 80% are generally needed for liquefaction. Tailings frequently have very degree of saturation because of how they are deposited, and hydrostatic conditions are uncommon, especially in upstream dams. What is your perspective on static liquefaction risk when tailings have less than 80% saturation? Are there accurate ways to estimate saturation in these materials?
Yeah, no, that's a great question, and I think it will allow me to say, perhaps to highlight a couple of things. Maybe let me share first some perspective over there and some information. That exact question, how to evaluate saturation or in situ conditions, did motivate a couple of projects that we recently developed at Thailand. So, and it's pretty much the projects were focused on getting a saturation profile on field conditions. So we have looked into different options for doing that, but I believe one of the emerging options is what I was mentioning before, NMR, nuclear magnetic resonance. So NMR can allow you to have an estimation of the saturation profile under some conditions. So we have evaluated a good number of tailings storage facilities, and it has worked, I would say, in a reasonable manner for most of them. But it can have also challenges when you have especially magnetic, units or magnetic materials in the mineralogy of the tailings. But NMR could be a good option to evaluate saturation profile. So that on what technique could be considered. Now, in terms of what to do with that, that's a more difficult question and perhaps going to be material specific. For instance, if we go into some of the existing literature, I don't think the 80% threshold is conclusive. And it should not be conclusive either, because different materials are different. So that number cannot be fixed for different materials with different properties. I think each material should be evaluated on its own context. Of course, 80% is kind of a ballpark, but now we have means to better evaluate what that threshold could likely be for a given material. A lot of work on that direction has been done by the Japanese, for example, when looking into the cyclic response of unsaturated materials. And depending on what you are doing, if you have, in the cyclic context, for example, if you have a high enough cyclic stress ratio, you will make the material, liquefy. If you define liquefaction as a number of cycles to get a given level of strength, even when you have saturations lower than 80%. So bottom line, very interesting topic. I don't think the 80% should be a fixed threshold. And in terms of what are potential techniques that could be used to measure saturation, take a look to NMR. I think it has potential.
Is the seismic design for TSFs also considered on traditionally non-seismic regions, or do they just focus in the high seismic areas?
No, it's actually, if you look into the new global industry standards for tailings management, in terms of seismic designs, 10,000 years return period is put forward into the discussions. So that makes that if you look, for example, into regions like Brazil, where I'm currently working and doing, I would say, significant seismic work. Brazil, think about Brazil in terms of the historical seismicity. Brazil is considered a continental stable zone. However, now seismic design is required. So when we look into 10,000 years, we may be looking into PGAs that are in the order of, say, 0.10, perhaps, maybe even up to 0.15. If you combine that with amplification that could be happening on subsoils, sometimes we have subsoils on tailings storage facilities foundations, or even, on the tailings that are stored. So that could be amplified significantly. We could, an example of that is the Mexico 1985 earthquake, where most of the, I would say, damage was due to the amplification of subsoils. So in short, countries like Brazil, even Australia, even South Africa, are looking into seismic design because the requirement of the 10,000 years return period.
Another issue that kind of comes up is I know when you're looking at soil liquefaction, for soils, it becomes less likely as the fines content increases. And I know if you have a significant gravel content, it's less likely as well. Is this also true for tailings or not? And, what parameters are correlated with liquefaction for tailings?
Yeah, no, another very interesting question, Ken, and I'll share my opinion on that. I think in terms of fine contents, I think it has little to do with liquefaction, actually, in my opinion. On the lab, we have been able to liquefy tailings with 100% fine contents, like, silt that are having very large fine contents. So I don't think, mechanistically speaking, fine contents is really telling us much about liquefaction. I think the key factor that, in my opinion, is a little bit overlooked is comprehensibility. Because fundamentally speaking, comprehensibility and strength, in addition to the latency, are the three aspects that are going to be influencing significantly the static and cyclic response of particulate materials in general. And static and cyclic liquefaction are just another facet of that, mechanical response of materials. So I think we should be paying attention to strength. We can get that from the CPT, for example. We can get that also from lab testing. Comprehensibility can be also obtained from the CPT. Stiffness is also important. That can be obtained from geophysical methods. So, and we should be, I believe, in my opinion, again, that's just my opinion, we should be departing from more, I would say, non-mechanistical descriptors like fine contents. There is nothing magical about, the amount of soil that is going through the 200 SIF. There is nothing magical about it. So it can be informative, yes, but is there anything fundamental or mechanistic about that? In my opinion, no.
Well, thank you. I do want to thank you for all of your time, specifically for putting the article together and for sitting with us here for the last hour. But I'd like to give you one more chance. What's your future what's your vision for the future of TSFs and tailings engineering, and anything else you might want to say in conclusion, to today's discussion?
Yeah, no, I think perhaps let me just highlight again what you have mentioned also, Ken, which you are mentioning that was highlighted on several of the articles on the GEOSTRATA magazine issue, and that is the need to train the next generation of tailings engineers. There have been several studies and publications, for example, There are some at CSU that were led by Chris Hatton, if my memory is correct, where and Kim Morrison has been very vocal about that too, and several industry leaders, that there is an imbalance between the demand and the supply of trained tailings engineers. So if you look at the amount of tailings facilities worldwide, and you look at the amount of geotechnical or tailings engineers in general, not only geotechnical, there is going to be an imbalance. So I think all of us as a community, we should contribute to train the next generation of tailings engineers. There are several initiatives for that, and I think all of them are needed. Thailand is one of them. There are several of them. And the idea is to collectively contribute to kind of fulfill that demand. So I want to highlight that aspect because I think it's very, very, very important. Then, going a little bit more technical, I believe that there is current research, for example, on dewatering technologies, going from, I would say, conventional tailings to, say, paste tailings or thickened tailings or even filter stacks. There are efforts on those directions that I think are valuable, but at the same time, we should also, in my opinion, take advantage of everything that we've learned as geotechnical and tailings engineers in the last several decades, because there is an important body of knowledge, for example, related to well engineering TSFs, that can, if those, I would say, lessons are followed to build or to manage the next TSFs, I think that's going to be in the advantage of the industry. So highlighting the lessons that have been learned from the good cases, I think is something that should be also considered, not only looking at the failures. Now, the other thing in terms of the future, I think AI is going to be having a key role as well. If you think about the amount of information that is produced, by the instrumentation or the monitoring of a TSF, is massive. If you look at the piezometers, if you look at the accelerometers, or you look at the remote sensing, and you look at the data that is produced in one single day is massive. So using AI to take advantage and to really manage that data on the benefit of the operation of a TSF, I think is going to be also something that's going to be, I would say, changing how we see the future of these facilities.
Okay, thanks. Thank you for wrapping this up. And I think at this point we'll get Brad back. I think he's going to have a few closing comments for us, and I'd like to thank everyone for attending.
Only a few, though, and they're not very intelligent or anything. So I hope nobody's bar was super high. And we're in the middle of a big thunderstorm here, so it got really dark. It was exciting, but thanks for a great presentation, Jorge, and for walking through all that. And one thing I love about GeoStrata, people will always ask me, well, is it a journal? And I always say, it's not a journal. And then is it like a popular magazine? And I say, it's not really a popular magazine either. But I think it provides a really unique forum for stuff like this, where, it's not even a quasi-technical article, but where you're able to kind of pontificate about the future. And we love having academics on here, too, because you guys can say whatever you want. You don't have to worry about anybody above you. So this is really good. I really appreciate that. And Ken, a great job with the questions, as always, for our viewers. If you liked what you saw, and if you're here at the end, you probably did, click like, subscribe, get notifications. Yes, we will. I mean it. We will let you know. It's automated, but we still will let you know every time we post something to the YouTube channel. Make sure you read those copies of GeoStrata, either the one that arrives in your mailbox or over at readgeo.com. We'd love to have your comments on any of that. Thanks for our questioners from the audience today. We really appreciate that. Our next live stream is in just 5 days. It's the next episode of Books Rock. It's GI's publication series. We'll be talking about the compaction grouting guideline. You can register for that and all of our other upcoming live streams at our Eventbrite page. So make your way over there and do that. Ken, Jorge, thanks so much, guys. Appreciate it. This was fantastic. And we will see everybody soon with another Geo-Institute live stream.